Welcome to Algebra 1, topic 10, working with functions. So the topic essential question would be what are some operations on functions that you could use to create models and solve problems? So the topic overview gives you an idea of how the topic is progressed. So starting with the square root and cube root function, we'll analyze functions graphically. We have done this a lot of times, but now that we have new functions, we could analyze functions graphically with the new functions. And then there are transformations of functions, translation, compression, stretches. And then the last two lessons will be operations with functions, with the function notation and the inverse functions. So let's start with lesson 10-1. So the square root function. In this lesson, we'll be able to describe the key features of the square root function. The vocabulary obviously would be square root function. So let's look at explore and reason. One of the strangest mysteries in archaeology was discovered in the Diguis Delta of Costa Rica. Hundreds of sphere-shaped stones were found. So the picture is a little bit cut off, but there is a big sphere over here. It's in your textbook. So you should have a big sphere. And then, a great circle is the circle with the greatest diameter that can be drawn on any given sphere. So in part A, the formula for the surface area of a sphere is 4 pi r squared. What is the surface area of the stone in terms of the circumference of the great circle? Yeah. So are we given the radius? Does the textbook? Okay, so let's see. Recall that the circumference of the circle is 2 pi r, right? Diameter times pi, right? So in terms of circumference, that means we're going to get rid of r and write it in terms of c. So we need 2 pi r, so surface area, SA, is 2 times pi times r, right? So we can rearrange so that it's 2 pi r here, then we have times 2 times r, right? And then that means 2 pi r is c, so then we can substitute that, but we don't want to use r. So we have to change that. So then we're going to change this circumference equation to solve for r so that we can write this surface area equation in terms of c, circumference. I know it's a little bit tedious, but let's solve for r with this equation. So r in terms of c would be c divided by 2r, right? 2 pi, yeah. So then instead of r, you're going to use that. C times 2 times c over 2 pi. And then 2's cancel out, so then we have c squared over pi. So then you can say surface area is equal to c squared over pi. Okay, so the circumferences of the great circles of spheres, part B, range in size from about 6 centimeters to 6 meters. Wow. Make a graph that represents circumference as a function of surface area. So, so we're going to let x be the surface area and then circumference be y. Okay. So then, if we let the surface area be the x and then circumference be the y, we know that using this equation, right? Surface area is equal to c squared over pi. Y is c, or we could let that be equal to x, but then it's not going to be, it's not going to be a square root function. So we're going to actually change this to a square function as a function of surface area. So we need to have a function of surface area actually. Then so then we could just type in the function equation. So SA, will let that be surface area be y, and circumference be x square all over pi, right? And then we have this curve. But then, our surface area in circumference can't be negative, so we're going to write where x is greater than positive. Okay, so then we have this graph, but obviously if we switched x and y, this is the first function, this one is a square function, right? But it's a quadratic function. But if we switch the domain, let's see, this is y divided by pi, where y is greater than 0. Then now we have a square function. Do you see that? Yeah. So this is when the circumference is the function, it's the y, it's the output. This is when the circumference is the input, and then we have a surface area, right? So this is how it's related. The square function is related to the square function. Okay, so let's look at part C. What similarities and differences do you notice about the graph from part B, the graph of a quadratic function? So obviously we're comparing this function and this function. What are the similarities? They look like the same function, just reflected across y equals x line, right? So yeah, that's the relationship. They're inverse functions. The graph appears to be half of a sideways parabola that opens to the right instead of up or down. So that's how I would word it. Well, we can say both graphs look like a parabola that open halfways. Square root function looks like a parabola, like a half of a sideways parabola that opens to the right instead of up or down, right? So this is a key characteristic of a graph of a square root function. So we're going to continue thinking about the essential question. What key features are shared among the square root function and translations of the square function? So let's look at example 1. Key features of the square root function. What are the key features of the function of square root? So this is the parent function of the square root. The function f of x equals square root is the square root function, the parent function of the square root function. So first, let's make a table and explore it. When x is 0, square root 0 is 0. And negative values are not defined, right? So you cannot put a negative input. You only have a positive x and 0. And in order to make it a nice little whole number, in order for your output to be a nice little whole number, your input must be perfect squares, right? So when x is 1, square root 1 is 1. When x is 4, square root 4 is 2, and so on. So the minimum point is 0, 0. The curve slopes upward slowly. So exponential function curves like this, right? Really exponentially quickly. But then the square root function goes up, but very slowly. The domain is restricted to x greater than or equal to 0 because only non-negative numbers have the real square root. So since the square root of a number cannot be negative, the range is anything greater than or equal to 0. And x, and because of that, your x values will be greater than or equal to 0 as well for the parent function. Yeah. So x and y-intercepts are both 0. The graph is increasing for all values in the domain of f. These are the key characteristics. So let's look at the try questions. Graph each function. What are the intercepts, domain, and range of the function? Pause the video, see if you can create a table and graph it on your own. Come back when you're ready for answers. Okay. Are you ready? Let's look at the first one. So if you look at the first one, you have a table of values x and y, or rather px, p of x. You have when x is equal to 0, you still have the same values like this, right? Except it becomes negative. But 0 is 0. But then if x is 1, square root 1 is 1, and negative of that is negative 1, right? So then the domain is still the same, but the output becomes all negative, right? So then we have all of these points. And so in the graph, you'll have the x-axis over here, the y-axis over here. You'll have 0, 0, 1, negative 1, 1, 2, 3, 4, negative 2, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 3, and so on. So then you have a curve like that. So what are the intercepts? X and y-intercepts are 0, 0, and then domain is equal to all values greater than 0, range. So for all y values, actually let's do p of x. All p of x values less than or equal to 0, right? So it's all negative. So similar to this one, you plug in everything, you'll get 0 divided by 10 is still 0, and that's 0. But then you have to divide everything, right? So in order for your root to be a perfect square, you need to multiply your perfect squares by 10. So then 10, instead of 1 divided by 10 is 1 over 10, like 0.1. And then square root of that is not a whole number. So then your next x whole number, if you want it to be a whole number, right, is 10. So then you have a table that looks like x values that increases really quickly. So then you have 10, which is the same input, right? And then 42, and then 93, 16, so 164, and so on. So then your x values just increase really quickly, right? So then you have 0, and this is 1, 2, and then but then you have 10, 1, and then 40, 2, and so on. So then you have the same shape, it's just stretched really, really thin. Okay, so those are the tables and graphs. I know the graph is not as accurate as I want it to be, but label your x and y axes and your numbers and your points. Okay, Let's look at example 2, translations of the square root function. How does the graph of g of x equals root x plus 2 plus 3 compare to the graph of f of x is equal to root x? So look at the graph here. You can graph each function. You can see that the orange one is a transformed graph, which goes up 3. So all the points move up vertically by 3 units, right? So for each x value, the corresponding y value is 3 units greater for g than it is for f. So then the translation vertically for 3 units up would be the translation, right? What about root of x plus 3 compared to the parent function root x? If we just look at it vertically, it looks like, oh, it's uneven. It's not even an even, maybe it's not the same function. But no, if you look at it horizontally, actually all the points are moving the same distance horizontally. So this point right here is moving this much. So it's moving exactly 3 units to the left, right? So then from here to here, it's moving 3 units to the left. So translation 3 units to the left. So let's look at try 2A and B. See if you can look at the translation and figure out if it's how many units it's translated where. So indicate the number of units and the direction. Pause the video, come back when you're ready for answers. Okay, are you ready? So part A, if you are not sure, you can always graph them and compare it with the parent function. This one, g of x, compared to the parent function, what do you notice? Should we graph? Yeah, let's do it. So g of x is square root square root. Oh, there we go. I forgot all these code names. X minus 4, right? And then your parent function f of x is equal to square root x. So compared to your parent function, all the points seems to move how many units? 1, 2, 3, 4 units down. 1, 2, 3, 4 units down. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So g of x is the graph of f of x translated 4 units down. And in the same way, p of x. Let's look at p of x. P of x is equal to square root of x minus 10. So we're looking at p of x, and compared to the parent function f of x, seems like it's a horizontal translation, 10 units to the right, right? So this function, parent function, moves 10 units to the right. This point, where's another point? This point moves 10 units to the right. And then this point moves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units to the right, exactly. So yeah, it's a translation 10 units to the right. P of x is the graph of f of x translated 10 units right. Okay, so if you don't remember how to figure out transformations easily by the equations, you should go back to the transformation lessons that were scattered throughout this textbook and practice transformations of functions using other functions, okay? Here we're going to look at the transformations of the square root functions in this topic. So let's look at example 3, rate of change of the square root function. So for the function f of x square root x, how does the average rate of change from x equals 0 to x equals 0.3 compared to the average rate of change from x equals 0.3 to x equals 0.6? So this is not a linear function where you have the same slope. Your slope is all different depending on which 2 points are you looking at. So we call this intervals. So the interval between 0 and 0.3. The slope is 0. The slope is like, I don't know this value, maybe like 0.55, right? 0.55 over 0.3. And so that's like 5 or 3, right? So, but then the slope here from the between the interval 0.3 and 0.6 seems like it went up like 1, 2, about 0.2 units, right? Over 0.3, right? This minus that. So then 2 over 3. So 5 over 3, very different. It's different from 2 over 3. So yeah, it's different. So for the square root functions, you can find the endpoints of each interval, use the slope equation to figure out the slope for that interval. So that is called the average rate of change, another word for slope. So we're going to use the word average rate of change a lot of times, but basically you can think of it as a slope. Okay, yeah, so the average rate of change over the interval 0 to 0.3 is greater than the average rate of change over the interval 0.3 to 0.6. So for the try number 3, for function h of x equals root 2x, find h of 8, h of 10, h of 12, and then find the average rate of change of the function over each interval. So first you have to figure out all the endpoints. Figure out what the value is for each of this input, and then find the average rate of change for the interval between 8 and 10 and 10 to 12. Pause the video, see if you can answer by yourself. Come back when you're ready for answers. Okay, are you ready? Have you figured out the points? So first of all, you need to figure out the points. So h of 8 is equal to 4, right? Is equal to 2 times 8 is 16. So root 16 is basically 4, right? So that's h of 8, and h of 10 is equal to about 4.47. So root 20. So I'm going to do is equal to root 20, but this is about 4.47. And then h of 12 is equal to root 24, and that's also about 4.90. So we have estimated the ones that were not whole numbers, and that's okay. We can still find the average rate of change, right? So this is each point. So we have 8, 4, 10, why is my pen not working? All right, 10, 4.47, and then 12, 4.90. So these are our points. You can figure out the average rate of change for each intervals using these points, these endpoints, right? So for part A, the average rate of change between the interval 8 to 10 would be 4.47 minus 4, which is 0.47, over 10 minus 8. And so that's about 0.47 divided by 2, which is 0.235, right? Now, using the same slope equation, you can figure out the average rate of change in the interval between 10 and 12. So 4.9 minus 4.47 over 12 minus 10, right? And so that's going to be 0.215. Yeah, 0.43 divided by 2 is 0.215. Okay, let's look at example 4, compare functions. Two plans are being considered to determine the speed of a theme park ride with a circular wall that spins. Plan A is represented by the function with the graph shown. The ride shown in the photo is an example of plan B. So this one is plan A, the one in the picture is plan B. If the ride has a radius of 3 meters, which plan would result in a greater speed for the ride? So for plan A, if it's 3 meters, the speed is about 6 meters per second, right? So this graph tells us easily that it's going to be about 6 meters per second. For here, we have an equation. So if it's 3 meters, f of 3 would be 5 root 3. And we need to figure that out. And if it's greater than 6, then plan B is greater. If it's less than 6, plan A is greater, right? So figure that out, which is about 8.7. So it's greater than 6, plan B is going to be a greater speed. So the ride using plan B has a greater speed for the radius of 3 meters. Okay, let's look at try part 4. To the nearest thousandths. So 3 decimal places. Evaluate each function for the given value of the variable. Pause the video. You have to substitute your input and figure out your output. So this is the function, and you're using these x equals 17 as inputs, okay? Pause the video. Come back when you're ready for answers. Okay, are you ready? Have you figured them out? All right, so basically v of 17 is equal to root 17 over 10 would be an exact answer, but you have to round it to the nearest thousandth, so it's going to be 0.412. W, so you can use a calculator for this. Don't worry, you don't have to solve it by hand. W of 17 is equal to root 17 over 100, but you have to divide 17 by not 110 first, so that's going to be 1.7. So root 1.7, right? This one you have to do the square root first and then divide it by 10. This one you divide it by 10 first and then do the square root. So then the answer is different. You have a bigger solution. You have a bigger answer. That's 1.304. Yeah. So the operations, the order of operations really matter. Okay. So do not mix them up when things are written specifically. So let's wrap up our lesson. So 10-1 was all about translations of the square function. The algebra will look like this, where you have a square root of x minus h plus k. So if it's if h is subtracted by, if x is subtracted by h in the square root, that is your domain change. And then if your whole function is changed by k, then that is your range. So domain is going to be moved to greater than or equal to h. Range is going to be moved from 0 to greater than or equal to k compared to your parent function. So your minimum point is obviously hk, where it starts your root function. All right, so yeah, with the specific numbers, for example, if you have root x minus 2 and then plus 4, then your domain will change from greater than or equal to 0 to greater than or equal to 2. Then y, range would change from greater than or equal to 0 to greater than or equal to 4. Now your minimum points would be 2, 4. So minimum point for x is 2, minimum point for y is 4. Right, so this graph is a horizontal translation of 2 units to the right and vertical translation 4 units up there are two translations here. Okay, so that was translations of the square root function. We'll continue with the next lesson in the next video.